Hello everyone, this video is brought to you by the Atılım University OpenCourseware project for the course Physics 101. The lecture notes are prepared by Associate Professor Dr. Hüseyin Oymak and the video lectures are prepared by Ümit Alkuş. In this video, we will solve one problem in Chapter 10. The three objects in the figure are connected by a rod of negligible mass. They rotate about the y-axis with angular speed 120 revolutions per minute. A. Calculate the kinetic energy of the system. B. What constant external torque is needed to increase its angular speed from omega 1, which is 120 revolutions per minute, to omega 2, which is 300 revolutions per minute in 6 revolutions. First of all, conventionally, we write the given quantities in SI unit system. Here, kilogram is already an SI unit. However, centimeters is not an SI unit and it is converted into meters. Also, revolutions and revolutions per minute are not SI units and they are converted into radians and radians per second respectively. Okay, let's start to solve part A. The rotational inertia of the system is found by this formula. Because we have three objects, then we write m1 times r1 squared plus m2 times r2 squared plus m3 times r3 squared. Now we can put the numerical values into this equation as follows. Therefore, the rotational inertia of the system is found to be 0.44 kilogram times meters squared. In the second step, we find the kinetic energy of the system as 1/2 times I times omega 1 squared, where I is the rotational inertia of the system, which is 0.44 kilogram times meter squared, and omega 1 is the initial angular speed of the system. If we put these values into the corresponding places in this equation, we obtain 3.52 pi squared joules. As a result, the kinetic energy of the system is approximately 34.7 joules. Alright, this was the first way to find the kinetic energy of the system. Now, let's discuss the second way. Here we use the relationship between the linear and angular speeds, which is V equals R times omega. Thus, the linear speed of mass m1 is V1 equals R1 times omega 1. Here R1 is the perpendicular distance from mass m1 to the y-axis, that is rotation axis. Omega 1 is the initial angular speed of the system. Now, if we put the numerical figures into this equation, we get 1.6 pi meters per second. Similarly, linear speeds of mass m2 and mass m3 are found as follows. Now, kinetic energy of the system can be found by this formula, which is the sum of the linear kinetic energies of each body. Therefore, we write 1/2 times m1 times v1 squared plus m2 times v2 squared plus m3 times v3 squared. Now substitute the numerical values into this equation. Then if you calculate, you find 3.52 pi squared joules. Then the kinetic energy of the system is approximately 34.7 joules. Notice that this result is the same as the one that we have found by the first way. To find the constant external torque in part B, again we can use two ways. The first way is the kinetic energy work theorem, which states that work equals to change in the kinetic energy. That is 1 over 2 times I times omega 2 squared minus 1 over 2 times I times omega 1 squared. And if we rearrange this formula, we obtain work equals 1 over 2 times I times omega 2 squared minus omega 1 squared. Here it is convenient to use the kinematic equation for omega 2 squared minus omega 1 squared, which is 2 alpha times delta theta, where alpha is the angular acceleration and delta theta is the change in the angular position. Then we obtain I times alpha times delta theta. Since I times alpha equals torque, that is tau, then we obtain tau times delta theta. We can find an expression for tau as tau equals work over delta theta. Now we use the expression for work, which is 1 over 2 times I times omega 2 squared minus omega 1 squared. Then the expression for torque is obtained as I times omega 2 squared minus omega 1 squared divided by 2 times delta theta. Now we insert the numerical values into this equation. Then calculation gives tau equals 1.54 pi Newton times meters. Finally, we obtain approximately 4.84 Newton times meters. Now, in the second way, we use the kinematic equation, that is omega 2 squared equals omega 1 squared plus 2 times alpha times delta theta. From this equation, we find an expression for angular acceleration as alpha equals omega 2 squared minus omega 1 squared divided by 2 times delta theta. Now, if we use the definition of torque, which is tau equals I times alpha, where I is the rotational inertia of the system, we finally obtain an expression for tau as I times omega 2 squared minus omega 1 squared over 2 times delta theta. As you see, it is the same as the result that we have found by the first way. Therefore, it is equal to approximately 4.84 Newton times meters. Okay, this result brings us to the end of the discussion of this problem. Thank you for your attention and see you in the next video.